We now consider a more complicated tank example here, where there's flow into one tank, but that tank then flows back into the original. We're also going to change the initial conditions to make things a little more interesting. And what we're going to get here is that one of the tanks, the second tank, starts very concentrated. And this tank here starts with no salt. Now we can use our intuition again to predict what's going to happen. Over time, the concentration, if we have 30 grams per liter coming in, both of them are going to eventually end up at that level. That's fairly certain. But what's going to happen in the meantime? Well, actually, we better move that 30 down a bit because one of them is starting at 90. That's our CB. So if we put 30 down here, one of them is going to start at 90, then it's going to flush water out to the sides, out to the first tank and out to the environment. So it's definitely going to go down. But the question is, will it plateau before it reaches 30? Will it dip below 30 and then come back? We don't really know in principle. We've got a good guess that the tank A is going to start at 0 and then go up, but will it overshoot and then come back down, or will it simply stay below 30 the whole time? We're going to need some quantitative prediction to be able to decide what's going to happen in this intermediate phase of the solution, or this prediction moment. With the goal of building a prediction in mind, let's go and create the differential equation for this system. So we've seen this before. The concentration is 1 over volume times the salt rate in minus the salt rate out. And these are going to be in grams per minute and grams per minute, so that'll be a guide for our units. What we get when we isolate tank A is that we have 1 over that tank volume. Inflow is coming from 2 places. So our salt rate in is going to be 7 liters per minute times 30 grams per liter. That's the inflow from this pipe. But there's also salt coming in from the second tank, and that's going to be an additive effect. We're going to add salt from there, and it's going to be 2 liters times whatever the concentration in B is. Liters per minute for the 2, that's the water flow, and it's going to bring with it whatever the concentration in tank B is in grams per liter. Then we're going to subtract the out rate. If you look at all the pipes, only one of them is flowing out to carry salt, and so it's going to be a term of 9 liters per minute times whatever the concentration in tank A is. Again, liters per minute and grams per liter, and we get grams per minute, which is what we want. Now we'll just tidy that up a little bit. And specifically, we'll break out the pieces that have C's and the pieces that don't have C's, and we'll use the 100 here. So we're going to get some decimal values this time. CA, we'll put that first. We have minus 9 over 100, so minus 0.09 CA, plus 0.02 CB, and plus 210 over 100 is 2.1. Let's call that CA prime. Perfect. Excellent start to things. We can do the same thing for CB. It's going to be 1 over the volume of B times the rate in minus rate out. And here, if we look carefully, the rate in is only from the 9 times CA. So we'll have a 9 CA. I won't put the units, it's exactly the same, liters per minute, grams per liter. And the outflow, there's 2 liters coming out this way, and there's another 7 liters per minute going out the other way, so 9 liters per minute total, all relative to the same concentration, CB. So we actually can accumulate these together and get a 9 for that. And if we use the value 50 for VB here, what we're going to get is positive 0.18 CA minus 0.18 CB. And that's CB prime. We'll copy these to the next page and then be able to easily translate that into matrix notation. Here are those same expressions again. And to turn it into matrix notation, we simply create a vector of CA, CB, the unknowns, and ask what's their derivative equal to. That's exactly what we have here. And then we put a column vector with those same two variables in them and ask what were the coefficients of those two values. Well, we have CA times negative 0.09, we have CB times positive 0.02, and we also have a 2.1. That ends up on the far right side here. In the CB equation, we have the same kind of pattern, except the coefficients are a little different, positive 0.18 and negative 0.18. There is nothing else left, so the non-homogeneous part there just gives us a 0. And so that's how we can move from a model like this, where it's all about flow rates and concentrations, to a mathematical presentation of it in a standard form of a first-order non-homogeneous system.